I will take it in a picture.
Yeah.
Super ball.
Maybe 2 rows or a circle.
Portfolio. Can you go closer? So we make two guys.
More people in front.
Yeah, this one is much better. Okay. Hello. Yes. Smile. It's not the video. Perfect. Okay.
Thank you.
Perfect. And now you have to invite me to a project that the picture.
Yeah. But we brought one together.
Yeah, yeah. Okay, so I think we can start. Sorry, take your seat and close the door. So I think we can start with this session now. I'm Fausto Gallucci, now from Eindhoven University, and I will share this session. And we have 5 projects, of which one is online. Okay, and so yeah, I would suggest that for the presentation we start with the project online. This is for later.
Yeah.
So we have Gonzalo. Gonzalo
Hello.
Lopez. Yes, we see you and we see also the presentation. So can you
Okay, perfect.
tell us what you do in CONFETI?
Okay, thank you very much, Fausto. Well, good morning or good afternoon. So I am Gonzalo Guirado, a full professor of chemistry at the University Autónoma of Barcelona, and I'm also the CONFETI project coordination. So I think that at this stage, more or less, everybody knows what we are doing in CONFETI, but just summarizing a little bit what we want to do in CONFETI. So CONFETI is a Pathfinder project, which is devoted to valorize carbon dioxide and nitrogen. So the idea of CONFETI is to validate or to build a new or to perform a new strategy in order to make more sustainable fertilizers. So for do so, what we propose in CONFETI is to develop 3 lab scale reactors. One of them will be electrochemical reactor, another one will be photochemical, and another will be based in macrofuel soil cells that we will see later. The idea is that using these 3 devices together to try to get in a more sustainable way the most common nitrogen-based fertilizers, such as urea, that will be our target product, but also ammonia. Just a brief reminder that everybody that we are working on that field. We know that the global market fertilizer now it's quite huge. So we are around almost $550 billion in worldwide, and in Europe it's around 72 billion, and it's expected to be increasing with a similar constant rate here around 6%, probably because of the demographic expansion and the increasing growing food demand that we have nowadays in our society. What we want to do here in CONFETI is develop a new strategy in order to demonstrate that another way different that Haber-Bosch is possible to make these fertilizers using more sustainable processes and greening routes. The first thing that we will do in CONFETI is just as Uriol yesterday told. So we will develop new membranes, as you can see here, in order to capture CO2 and nitrogen directly from the air. So once this CO2 is captured or the membrane is doped by nitrogenate compounds, we will introduce these materials onto electrochemical reactor. So this electrochemical reactor that I think David explained yesterday, and also Pamela a little bit this morning. So the idea is to include this type of membranes inside the reactor. So we will have the CO2 capture material inside. We will ameliorate some electrolytes in order to make those membranes at the same time a capture material and electrolyte. And we will also make a library on different electrocatalysts that can allow us to produce the urea. So when the urea is formed with the electrolyzer, we plan to deliver this urea into the field. But before to do that, the idea is that to trigger the electrochemical reactor using renewable energy sources. In this case, we select soil fuel cells. So we will collect the electrons from the bacteria, and from these electrons, we will trigger the electrochemical device that we produce urea and we deliver directly into the field. Since it is known that not all the quantity of urea that we will deliver to the field will be absorbed by the plants. So we are designing a recovery system, which in principle is based in solar photocatalysis using these CPC solar photoreactors that Ilaria explained yesterday morning in the season. And for doing that, we select different photocatalysts and different materials. So at that point, we were able to make the first, we can say, portable CPC photochemical reactor using sunlight. So with this reactor, we recover the excess of nitrates from either leachates or agricultural wastewater, and then we irradiate with solar light and we convert this excess of nitrates into ammonia, and then we can have two uses of this ammonia. Either we can just save it, or we can just directly apply also to the field in order to use this as a fertilizers. So for doing so, we have a very nice team and very good partners, and they are doing a great job. So we have partners from different countries, as you can see here, from 5 different countries, from Spain, France, Italy, and Belgium. And also we have an associate partner for United States from Iowa State University. So most of the partners are involved in different stuff of the project. So I think that the electrochemical reactor that we present, so for instance, is developed by UWamper University, by LCAP Group, with the help of CNRS and UAB. The photochemical reactor is being developed in the Plataforma Solar de Almería with the contribution of the UAB researchers, and the microfuel soil cell is also performed by UAB, CSIC, and Bio, which is a company which is specialized in this type of technology. So what we expect at the end? So at the end, we went to try to produce an autonomous system for deliver and make nitrogen fertilizers. So we want to do it using renewable sources. So we select microfluidic soil cells, as I just pointed before, but also if it's needed, we will use solar panels in order to get more power. Now the use of solar power is a quite common technology in agricultural practices. With the design of these different photo and electrochemical reactors, we will try to minimize the use of raw materials. And the main idea that we will focus on is to produce and deliver in situ the fertilizers. So if we can able to do so, we will able to reduce a lot of costs related with packaging and storage, and also with transport and other and spreading. So this is more or less the overview of CONFETI. So I think that along these 2 days, you have already seen how these technologies are being developing in these past 2 years, and we hope we will have a fully equipped system by June, July, before these summer holidays. So thank you very much for your attention and for giving us the opportunity of showing what we are doing in CONFETI, and also of sharing the different interesting investigation that we have seen those days. Thank you very much.
Thank you very much, Gonzalo. Now we come back to the room, and we go on with Mara. We present
Yes.
MINICOR.
Hello, I am Mara Joannou from the Institute of Science and Technology of Sustainable Energy Mobility of CNR Italy. And I think that many of you already hear something about MINICOR, but I just do a fast recap. I am not the coordinator. The coordinator is involved in another meeting that not skip because is a meeting organized by himself for an association at ECHE. So it's quite impossible to skip it. So MINICOR is a project belonging to again a portfolio looking at CO2 and nitrogen valorization and management. And so it is a IC Pathfinder project. It started in 2023 and it will end in 2028. So we have there is still a lot of study to do. What is the idea behind MINICOR? MINICOR aims to develop an integrated process that use waste and residual biomasses to build a value chain for the production of biochar, syngas, and energy. Of course, utilizing with the utilization of CO2 and for nitrogen uptake. The consortium is reported here, so we are 4 institutes, 3 countries, Sweden, with the Lund University, where there is the coordinator, that is Christian Brackman, RISE, and then Denmark with DTU and CNR in Naples. I have to say that this is a very strong interaction within the project in all the activity that will carry on during the development of research activity. What is the idea behind that? Or the concept, how it can be developed? It is developed in this scheme. So we start from carbon-based feedstock, also manure and so on, and we pyrolyzed this feedstock with CO2, and we have, of course, 3 products. That is biochar, biogas, and bio-oil. Biogas and bio-oil are intermediate products because we want to, that it's very difficult to use directly bio-oil, so we process it again with dry reforming, non-catalytic dry reforming. So we design with utilization of CO2 and heating the process by utilization of biogas by means of mild combustion. After I will say you something towards more on that. And so we obtain syngas, maybe energy. And on the other side, we have biochar that will be activated with CO2 and to be utilized for nitrogen uptake and to be used as, for example, soil carbonization and nitrification. Of course, this is when I look at soil carbonization nitrification. This is our first point that we described in the project in the proposal. But biochar now we are looking for biochar many other applications. So the project is divided in different groups. The first one is focused on pyrolysis, so looking at the effect of, for example, temperature or carrier gas on the products. Then on mild combustion and reforming. And it is very important here the coupling of these 2 processes, because mild combustion allows us to use very low calorific value gases that coming from pyrolysis without further upgrade. And So the coupling of these two processes is very relevant in case. And the other point, the other two VP are focused on the modeling both of pyrolysis process and of mild combustion and reforming, both from kinetic point of view and system point of view. And then there is the UP5 for the characterization of biochar and functionalization activation, let's say, activation of biochar. And as discussed this morning, we have UP6 late in the project, so we have not yet started that for life cycle assessment analysis. So what is the for summarizing the MINICOR approach? Because we have the co-production of syngas and biochar using biomass residue, so it is a efficient process with respect to resource. There is an energy integration. I mean that we aim to be to reach a self-sustainable process. And of course, there are some environmental advantages with carbon sequestration, CO2 utilization, and soil nidification. From technological point of view, as I said before, it is very important the integrated process of mild combustion with dry reforming that gives us the opportunity to use very local empiric value, and because I say we have two problems. The system is flexible. I mean, we can optimize the process and maximize the characteristics that we require to biochar or to the syngas. The other point is that we do not use, this is why we choose non-catalytic dry deforming critical materials. So that's all. Thank you.
Thank you very much. I will continue with George. Yeah, for the ECOLEFINS.
This is for you.
Good afternoon, everyone.
Yes.
So I am going to present the ECOLEFINS project. My name is George Marnellos. Together with my colleague Kostas Athanasiou, we are coordinating this project, where the motto is to detach the petrochemical industry from the CO2 emissions in just a single device, not so many devices, in just a single device. So it's a project that has been funded by the European Innovation Council, Pathfinder Open. The total amount of funding is around 3 million euros, and about $500,000 is coming from the UK Research Innovation Council. And it had, let's say, a duration of 3 years. The project will be completed at the end of September 2026. So our target is to produce light olefins. Light olefins are platform chemicals where we can produce many things that we are using in everyday life. For example, plastics. So they are very important in the economy, not only of the EU, of the world. The commodity price is about 1,000 euro per ton. However, currently, the light olefins are produced by the steam cracking of naphtha. Naphtha is a distillated product from the crude oil. So it is accompanied by CO2 emissions. And you can see here that around 5 to 10 tons of CO2 are emitted when we want to produce 1 ton of light olefins. So what is our answer to this challenge? This is our concept. Our concept is comprised of an electrochemical ceramic reactor which is comprised from the two electrodes, the cathode and anode, and in between of those two electrodes, there is the solid electrolyte, which is not a usual solid electrolyte. As you can see, it conducts both oxygen and ions and protons. So in this single device, we are feeding this device with CO2 and water, two adjutant and cheap raw materials, and we want them to be converted to light olefins. In this device, as you can see, we have also a heat integration, because on the one side, we are doing the endothermic steam electrolysis, and on the other side, we are doing the exothermic CO2 hydrolysis to light olefins. So let me describe a little bit more. So we are feeding CO2 at the cathode, and we are feeding water at the anode. And by applying a certain voltage or a current, we can remove protons from the water and feed the protons through the ceramic electrolyte to the cathode, where they will meet CO2, and hopefully they will give, let's say, light olefins, but also some other products. So our long-term impacts, if this is a successful technology, and we hope that it will become a successful technology, is, as I said before, to decouple major petrochemicals from petroleum, to expand the light olefins production to end user, because this device can be applied in small scale, let's say, applications, but also to large scale applications. This is a modular technology that is easily to be scaled up. At full deployment, if we imagine that we are going to use this technology to replace the common practice for the production of light olefins in Europe, we will save and capture up to 20% of industrial CO2 emissions. We will, from some first calculations, we have calculated that our approach, compared to another low carbon approach, which is to have a separate water electrolysis unit and a separate compressed reactor, we have calculated that we need half of the energy, electrical energy, compared to the other low carbon alternative. And at full deployment, we will need more and more renewable electricity. So some first calculation, we need an increase by 25% of the total EU electricity demand. So our concept matches very much with the electrification of the industry. And this concept is planned to be realized by a wonderful team. We are 8 partners from 6 different countries. From Greece, we have the CERT, which is the coordinator, the Technical University of Crete, which deals with catalysis, the Hellenic Energy, which is the biggest petrochemical industry in the southeastern part of Europe, the Politecnico di Torino with modeling, Jülich for the Jülich and St. Andrews, University of St. Andrews for the electrodes, but also for the co-ionic electrolytes, the University of Groningen from the anodes, and Elcogen, which is a high-tech company from Estonia, which builds such stacks that we want to build in this project. So what we have done so far, and what we are thinking that are the main breakthroughs up to now, we have developed single-phase and dual-phase co-ionic electrolytes. This means that they can conduct both protons and oxide ions. And this development has been guided by VFT modeling, where there is a poster in the other room from Severin Kufer from Jülich, and they suggested to substitute, to have a substitution in the standard BCZY proton conducting electrolyte with scandium, and we verified this experimentally, that we are observing the desired co-ionic conductivity. We have developed materials for the CO2 activation electrodes. We followed 4 different routes. And yesterday, Michalis Konsolakis from the Technical University of Crete presented the efforts for the development of cobalt iron unsupported catalysts. And we have also developed water dissociation electrodes. Vasilis Kyriakou has at 3 o'clock, I guess, a presentation for the anodes. And finally, we have 2 CFD simulation studies. You saw the presentation by Andrea Morenti in order to build a short stack of 2 to 3 repeating units. And what we are also proud is that the ULIC partner has produced for the first time, I guess, 5x5 co-ionic ceramic planar cells. This is very, very, let's say, interesting and very, very important for our project. And of course, the last work package is dealing with the assessment of the technology, which includes the techno-economic assessment and the life cycle social and life cycle assessment. So that's all from my side. Thank you. You can visit the site. We have some social media accounts, and you are welcome if you want to cooperate with you. Okay.
Thank you very much. We will continue with Anita now, the CUMERI project.
Okay, so Anita Bückert from Witwer. I'm coordinating Horizon Europe project CUMERI, which is an innovation action. So we go to full piloting. The driver of CUMERI is actually to resource recovery, getting more and more closer to circular processing, and also and at the same time CO2 reduction. It can be or by CO2 capture or by avoiding CO2 by using less energy. Now we do this using membranes, and in this project we use 4 different membrane platforms, quite flexible ones that were already developed up to lab scale, and that we will bring from lab to pilot in this project, so from 3 to 7. And we focus then on 2 economically attractive separation lines. One gas separation line, which is the recovery of hydrogen with CO2 capture from coke oven gas in the steel industry. And there is a liquid filtration line, a quite different line from the oil and gas industry, where we develop a membrane alternative for redefining of used lubricant oils. So you see the scheme summarizes it all, let's say. We have a nice partnership of about 16 partners. We have also a Swiss partner who luckily brings his own money, and we have also a few Turkish partners. We have, of course, two industrial partners we work with in the gas separation line. It's the steel factory Eindhoven in Turkey, and for us in the liquid filtration line, it's also the French refiner. Okay, let's take a bit deeper in the 2 lines and the technologies that I'm talking about. So for the gas separation line, we intend to use the coke oven gas coming into a membrane unit with ceramic membranes that will recover the hydrogen that can be reused for the reduction in the steel factory. Then we go with the redentate to an oxy-combustion, and this produces, of course, a gas with quite high amounts of CO2, which is perfect to go into polymeric membrane modules for the CO2 capture. And so you see down there the developments on the silicon carbide nitride membranes for hydrogen separation. So it's a collaboration between the Saint-Gobain who develops the membranes, and Fraunhofer IKTS, who develops the top layers of these membranes. On the other hand, for the polymeric membranes, we have Technalia working together with the University of Maastricht for the tuning of this polyether block polyamide membranes, specifically for CO2 capture. And they want specifically also to bring them into not flat sheets, but hollow fibers to profit from this design. For the liquid line, we are working on this used lubricant oil that is nicely collected in Europe. And we thought first that we need a pre-treatment, which turns out afterwards not to be necessary. So we remove the water in the UF plus ME membrane extraction membrane steps afterwards. So we have been looking to the support materials of Rauschert, and we can tune them with Fraunhofer, but it was actually not needed to change these. But we did look a lot to different crafting techniques, and we scaled also some of these techniques up to get to the best membranes of this application. We started in December 22. We are now 3 years forward. We still have half a year to go, which is mainly focused on the gas separation piloting. So we have done in the beginning of the project already some preliminary economic and environmental analysis. And of course, then we have been developing the different materials, the different membrane platforms, and selecting the right ones for the applications mentioned. And we are now more or less at the end of the upscaling. And we did already quite some testing in piloting in the liquid line, and the gas separation line will start very soon. And of course, with the results coming out there, we will revisit the LCA and the academic evaluation. I think this was my presentation.
And now we have Martin. No.
I'm
Representing.
yes, let's say it like that. So
Yeah. So, but I don't. I have the other name.
Yes.
It's Iconic project.
Yes. So Ruud Kortlever, I'm associate professor at TU Delft. I'm not the project coordinator, as you already know now. Project coordination is at ICFO in Spain. Brian Garcia is the main program lead. But I'm representing the project today, so I'll give you a very short overview of what we are doing. We're a Pathfinder Challenge project, working on circular fertilizers from polluted seawater, so Iconic integrated conversion of nitrate and carbonate waste streams. That's where it stands for. So problem was faced, really something that came up. Well, a lot of the European seas suffer from excess of nutrients, nitrogen or phosphorus-based nutrients, leading to eutrophication. And at the same time, we are currently making fertilizers in a very energy-intensive way that also causes a lot of CO2 emissions. So 2% of the global CO2 emissions come from the Haber-Bosch process that makes urea. And then with urea plus CO2, you make, that makes ammonia. With ammonia plus CO2, you make urea. So what now if you could use waste streams, such as this contaminated seawater, and convert that directly into the end product, urea as an artificial fertilizer. So that's the main goal that we want to do. In Iconic, here you see the proposed solutions. We use an electrochemical cell, so it's all an electrocatalytic process. So you can make decentralized units that can actually convert our reactants into urea. Initially starting from CO2 plus nitrate. Eventually, at the end of the project, we want to use real contaminated seawater streams contaminated with carbonate, and then converting the carbonate with nitrate to urea. And the envisioned solutions that we are aiming for, and of course not directly at the end of this project, but this should lead to the base technology to make these kind of solutions where you can actually have a treatment plant that could convert contaminated seawater to a fertilizer that can so results that we are aiming for. So in this project, we are developing catalytic materials. We're developing the electrolytic cell. We're trying to get ideas on how this reaction actually goes, the fundamental way. And at the end of the project, the main deliverables have to have a prototype that can use a real contaminated seawater stream and convert that into to urea. Now, of course, the economic and environmental impact already mentioned, right? You want to go to a circular fertilizer value chain, and then, of course, can also improve the ocean health to reduce the CO2 emissions. Yeah, so with that, there's a lot of different partners involved. So I'm representing TU Delft. ICFO is the main project lead. We have ICN2, ICMA in Spain, TUM, Technical University Munich in Germany, CSC Eindhoven, now also in Spain, all involved. Trinity College in Dublin is also involved in this project. Yeah, so that's a short overview. If you have any questions about the project, you can always feel free to approach me later.
Thank you very much. Let me put also. These are the answers to the possible questions, I guess.
Yeah.
Okay, let me change the question then.
Yeah.
Yeah. So I have the questions that you also have, but I want to change a little bit because this morning I was not allowed to ask a question, which I'm still waiting. But no, it's true. And I was impressed. I want to start with Anita first. Yes, Gonzalo, you hear us?
Yes.
Yes. Okay. So I will have also some questions for you. I want to start with Anita because I was impressed. I was still impressed by the fact that you have a work package 1 of 6 months doing LCA, and then you say we did the material based on the results of this work package. So I mean, remember. So how did it work? Because in many projects the LCA is at the end.
Yeah, of course, how different than a lot of these low-terrel projects here. We start from things from membrane technologies that were already shown in the lab to work. So we start from something. We have already a quite good idea how they are made, how they are produced, and what they deliver. So both in the economic and social and environmental analysis, we use this knowledge, of course, and we use, at least in both, we use also sensitivity analysis to vary the parameters that we don't have a good grasp of. And so like selectivity, like fluxes, these things, or membrane price, membrane lifetime, we do sensitivity analysis there. And this gives actually, I've seen it working in many projects that I've been involved in lately, and it gives a very interesting information. You can see, for instance, that in both lines that we have here, if you have membranes that have very short lifetime, shorter than 5 years, sorry, then your costs are your environmental or economic is skyrocketing. Once you have 5 years, it's it's actually not improving a lot. So 5 years is nice to know, and you get also similar ideas on good fluxes. We know, for instance, for the liquid line, that above a flux of 5, I think it was kilograms per square meter in this case, it also doesn't change a lot. And that's how we used this also in later developments.
Okay, thank you very much. I will come back to this as well. For the others, how it works with LCA? Do you have feedback loop in your projects? Perhaps, Tamara?
Of course, we have planned the LCA in our project, but as usual, as you said, it will be at the end of the project because we need several information by the subsystem that are involved in the project. However, I understand very well what you asked, Anita, because it's important to have an indication. So a preliminary, a sort of preliminary LCA. So we do not do an LCA, but I this morning presented this part of work about a preliminary analysis with the Aspen that is not really an LCA, but allowing us to have some indication on how to proceed in some units of the process. So this is, but we will have the final LCA when we finalize the characterization of the different steps of the process.
And if the LCA tells you that your technology is more polluting, then what are you going to do?
I think that it is not, but because
we always say.
Yes, no, but you know, we use different steps that should be not polluting. Also, the step that is mild combustion, because we generally look at the combustion as polluting technologies, but this is I presented yesterday. It's a different kind. I say the other side of the combustion because it works at a very low maximum temperature, so below the threshold for the formation of main byproducts, so soot or nitrogen NOx emission. And so from this point of view, I would say that is we are comfortable that, however, in case we could add units, it is very interesting here to discuss with other projects because they could be the solution of some potential problem with the pollution.
Let's go to Gonzalo. Can you tell us a little bit how you are using LCA?
Yes, of course. So we are, since as you know, we have 3 different devices. So we are analyzing every device separately. So first, we have already performed all the life cycle assessment of the CO2 capture materials, which are based in ion gel. So we have already performed that. And now we are also replacing, because we are adapting the different information that we get in order to ameliorate the process, how we synthesize those materials. So far we have replaced some solvents in the synthetic procedure. We are also analyzing the way we are packaging the microfuel soil cells. So far the containers, they are made from polylactic acid. So we are also looking for alternative in order to see how we can improve their production. And in the case of a photochemical reactor, here is more difficult to apply the things because somehow you are restricted to the materials that we are used. So the photocatalyst sometimes is difficult to replace, right? Because at the end, we want to make the process, but we are trying to ameliorate the external components that we are using for fabricating the whole device. And in the case of the electrochemical reactor, is more or less the same. So we are analyzing all the different materials that we are using for making each compartment. And at some point, if it's needed, so we will try to use more sustainable materials. Also with the electrocatalyst, we are trying to look for the ones that are not raw or critical materials in order to enhance and to be more sustainable with the things that we are producing. But we are doing it in a continuous way because if we have all the information at the end, as just has been pointing, so then we don't have time to try to replace or ameliorate the process, right? So this is more or less how we are face that problem.
Thank you very much. And from your side, George?
So, in order to be honest, actually, we have also the LCA task at the end, but actually it runs from the second year until the end of the project. We are, let's say, seeing on a system perspective, the life cycle assessment on the materials. Our concept, we say, and we believe that it is a carbon negative, not only carbon neutral, but carbon negative. So the main thing about the materials and the design of the materials, I think that it is to try to avoid critical raw materials, because we may find technologies to use renewable energy, variable renewable energy, which is abundant everywhere. So to be independent of energy imports, but then we will be dependent of material imports. So I think that we should also not only thinking of the life cycle analysis of the materials, how we can extract these materials and use materials and treat materials. We should think of recyclability of materials after the end of life of the equipment, but also try to decrease the amount of critical raw materials.
Yeah, I can comment a bit about what we are doing. I think LCA for us is a bit more towards the end of the project. We are, of course, more now demonstrating the proof of concept for the entire process. And I think what is very valuable for us, and it's the work that Simeon will present this afternoon as well, is to have a sort of idea of how a process would look like, to actually have a process model and to be able to compare what the actual energy inputs would be compared to traditional, what the cost would be to compared to traditional, what the CO2 emissions would be. So that would be more a life cycle analysis as well on the process, compared to traditional process.
Okay. But if we continue on this, if I understood well, your process should be more distributed, right? You are not decentralized.
Yes.
So is then fair to compare to a conventional process where it's multi-ton, million-ton per year?
Well, you can of course already ask the question: is it fair to compare our new process to something that has been developed for about 100 years? Right? So has been around since 1920.
Yes.
So already that's maybe a not so fair comparison.
Although before that, ammonia was produced with electrolyzers.
Yeah,
So,
yeah. And even before that with plasma, you could. So, yeah.
Okay. So what is the scale of the process? Suppose that you go up to commercial application. What you envision for your process in particular?
Yeah, I think that's a very good question. I don't think that we have a defined actual process scale. So I think this kind of electrochemical process, in my opinion, will only be a decentralized option. So it will never be the same size as our Bosch has, or the Meister process. But the eventual end scale, I think, is also very difficult to now say, because it will also depend, I think, on the entire process and the process optimization in the entire process. So maybe we'll find out that we actually have a minimum scale to make our process energy efficient.
Yeah. Okay. So perhaps the same question goes for CONFETI. What is the size that you think will be your?
Yeah, it's a very good point. So we have, I mean, at that moment we have like different, we can say different levels of scalability. In the case of the photochemical reactor that we are recovering, the wastewater from agricultural fields, so we are able. Well, we have already designed the photochemical reactor, which is portable, and we are able to treat between 5 and 25 liters. So that's a quite, we can say, more than lab scale device. In the case of microfuel soil cells, we can also have more than lab scale device, because we can have like 4 different batteries that we can connect in parallel in order to get the highest amount of electricity. So then it's also we can say more than expecting at the beginning. But in the case of the electrochemical reactor, we are still in more laboratory scale device. So the production that we expect is around 100 milligrams of urea per day, as Davide pointed yesterday. And for that, I think we can treat like a small, we can say, garden or for as a proof of concept. That's our idea. That in fact we have already the place where we will locate the batteries for testing this the three devices together and separately.
Yeah, thank you. I think this is all. So I think you have the most difficult application,
Yeah.
because you want to replace something that is huge, yes, to produce something that is used in huge quantities.
Yeah. And it's good. Let's say in the framework of the project, we would like, let's say, to build something around 1 kilowatt stack, which will be comprised of 2 to 3 planar cells in a window frame, as you see. So they will have 5 by 5 cells in each window. And the question is how we are thinking our technology. Yes, we also advertised that we can bring light olefins to, let's say, to end users, to small, let's say, to decentralized units. Because also we should also think about the availability of renewable electricity and the huge amount of solar panels that you may need and the wind, let's say, farms. And it's not only that, because if you go and do the economics, you should, let's say, calculate the substations that you need, the transmission fees and cost that you need for that. So I guess that it could be, let's say, to, I agree with Ruud that this electrochemical processes fits to small to medium, let's say, scale plants.
Okay, so in principle, in the future, we will have ethylene on demand.
Yeah,
that's a nice. I have a question for Mara, because today I learned about yesterday about this mild condition combustion without flame. So you combine this combustion and the reforming, but you say that is non-catalyzed, right? Yeah.
we give you the.
No. I'm just getting out of buckets. So
Yes. The point is we will to design the coupling of the two systems. That is a challenge, of course, because you have to transfer the heat to the dry reforming unit. So this is the key challenge. The point is using a mild, because as I told yesterday, it is a really flexible system. So I can have a wide range of composition as biogas input that it just strongly depends on the feedstock that you use. And so I can have different biogas with different heating value to be used in the same unit, because we use for stabilizing my combustion, you have to design properly the enough field inside the reactor, inside the burner. And in our case, we use a special kind of system that allow us to stabilize a cyclonic flow. that is really stable and allow us to change in a wide range of calorific value the fuel. I told you yesterday we are able to stabilize ammonia up to hydrogen without changing any let's say hardware part of the system, so keeping the same facility. This is this is the strong the one area to join to couple these two systems, because we can use a byproduct that is not of strong value, let's say biogas, without upgrading it and for reforming the biogas.
Yeah, you told me before that you can burn ammonia 100% without,
Yes.
which is amazing. I didn't know that was even possible. I want to come back to Anita, what you were mentioning, because I saw that you do very nice, almost 1 year of testing with the 2 lines, right? Okay. I have to do the other one with the 2 lines, and you almost finished the first evaluation, and you were starting with the gas separation line. But you also mentioned below 5 years, a lot of problems, and after more or less is stable. How do we convince that with a few months test that the membranes will last for 5 years? Do you have any idea?
Yeah, from the liquid line. Yeah, we have been testing, of course. Now we know in general ceramic membranes in this liquid, even in this liquid environment, are quite stable. And from our 3 months that we did now, or 4 months that we did with piloting, we really can say that these membranes are acting really very stable. We know also that they can be reused easily with very simple permeate flushing with backpulls only, let's say, each 12 hours. You can get your flux stable. We know that we can chemically clean them very well with xylene in this particular case. So 5 years should be really possible. From what we have seen, this is really for the gas line, that's something else. Now, we chose, of course, these both type of membranes, the silicon carbide membranes, carbon nitride. I think you saw the presentation of Hannes yesterday. This nitride also adds to the stability. Silicon carbide in general, very stable material. So I think they're also maybe we plan a pre-treatment on the coke oven gas, but it's also the idea to see what is needed and not needed, because we think the most difficult is probably tar there, which of course is a killer for all gas separation membrane. So for the silicon carbide, this looks like also very good. For the beta membranes, they're also made to be, the PE part is for the CO2, to increase the CO2 selectivity and flow, and the PA part is there also for the stability. But there also we will need pre-treatments, that is for sure, in this CO2 nitrogen separation. And maybe this is, in view of lifetime, maybe most difficult to define. But I think, I do not know, but the Tecnalia people have a lot of experience with this particular material, tuned in a different way, because that's PIPA is flexible. There have been many other projects, the same membranes running. So there's maybe already info that I'm not aware of.
So in view of time, I have a last question. Perhaps Ruth, you can Help us. When I was a master student, there there were a lot of professors doing electrochemistry. And then when I was PhD student, most of the group closed because apparently everything was known and there was no money for these people. So, and now many people are working on electrochemistry. How do you see the future of electrochemistry?
Well, I have the same experience. So when I was a PhD, there was one group in the Netherlands doing electrochemistry. I think now every university in the Netherlands has electrochemistry, and you see this trend throughout Europe. I think electrochemistry has a very bright future. I think we've come from a past where we had one solution for everything, fossil-based processes, fossil resources, fossil fuels. In the future, we'll need a lot more different varying technologies, and I think electrochemistry can play a role. I don't think that electrochemistry can play a role in all of these kind of parts, but it will definitely have a role. Especially, I think, for these decentralized options, electrochemistry is very strong, because basically you don't need a lot of heat integration, you don't need a lot of complex integration processes. Yes, and it also can work with intermittent energy inputs. So I think that there we can use the strong suits of electrochemistry. So I think it has a bright future.
Yeah. Yes, absolutely.
One more to add. Yes, there is a great future in electrochemistry since we want to electrify everything and we have abundant electricity. And also with electrochemistry, we can do some magic, which with the conventional technology, you cannot do this. So that's why I see a great future in electrochemistry.
Thank you very much. In view of time, I want to thank you again, panelists. Thank you very much, Gonzalo. And we will continue now with the two sessions.
The ECOLEFINS partners, can we make a photo?